Another significant and full of new learning again, everyone. Our lesson for today is about numerical differentiation and integration. Our learning objective for these lessons are to define numerical differentiation, to determine the numerical value of a derivative of a given function at a given point using an appropriate method, approximate computation of an integral using numerical techniques. So let's first discuss numerical differentiation. Introduction. Calculus is the mathematics of change. It is an essential tool that continuously deals with systems and processes that change. The heart of calculus is related mathematical concepts of differentiation. Derivative serves as the fundamental vehicle for differentiation, representing the rate of change of a dependent variable with respect to an independent variable. It begins with a different approximation as shown in equation PT 6.1. Delta y all over delta x is equal to the function of x sub I plus delta x minus function of x sub I all over delta x, wherein y and the function of x are alternative representatives for the dependent variable and x is the independent variable. If delta x is allowed to approach 0, as occurs in moving from the figure PT 6.1a to c, the difference becomes a derivative, as shown in figure PT 6.1. So the graphical definition of a derivative as delta x approaches to 0 in going from a to c. The difference approximation becomes a derivative wherein the delta x approaches to 0, where delta y, wherein the derivative of y with respect to x, which can also be designated as y or the function x sub I, is the first derivative of y with respect to x evaluated at x sub I, as seen in the visual depiction of figure PT 6.1c. The derivative is the slope of the tangent to the curve x sub I. The second derivative represents the derivative of the first derivative. Thus, the second derivative tells us how fast the slope is changing. It is commonly referred to as the curvature because a high value for the second derivative means high curvature. So, non-computer method for differentiation, the function to be differentiated will typically be one of the following three forms. The first one, a simple continuous function such as polynomial, an exponential, and a trigonometric function. The second one, a complicated continuous function that is difficult or impossible to differentiate or integrate directly. The third, a tabulated function, where values of x and the function of x are given at several discrete points, as is often the case with experimental or field data. In the first case, the derivative or integral of a simple function may be evaluated analytically using calculus. For the second case, analytical solutions are often impractical and sometimes impossible to obtain. In these instances, as well as in the third case of discrete data points, approximate methods must be employed. Equal area graphical differentiation. A non-computer method for determining derivatives from data is called equal area graphical differentiation. In this method, the x and y data are tabulated, and for interval, a simple divided difference of delta y all over delta x is employed to estimate the slope. Then these values are plotted as a stepped curve versus x as shown in figure PT 6.4. Next, a smooth curve is drawn that attempts to approximate the area under the stepped curve. That is, it is drawn so that visually the positive and negative areas are balanced. The rates at given values of x can then be read from the curve. So we have here figure PT 6.4, the equal area differentiation. For figure A, center finite divided difference are used to estimate the derivative from which interval between the data points. And for figure B, the derivative estimates are plotted as a bar graph. A smooth curve is superimposed of this plot to approximate the area under the bar graph. This is accomplished by drawing the curve so that equal positive and negative areas are balanced. And for C, values of the derivative of y with respect to x can then be read of the smooth curve. So let's have a mathematical background. Table PT 6.1 are some of the commonly used derivatives. So we have here the derivative of sine x with respect to x is equals to cosine x until the derivative of a raised to x with respect to x is equals to a raised to x ln a. So before discussing the high accuracy differentiation formula, let's have a brief review on using the Taylor series to estimate truncation errors. Although Taylor series will be extremely useful in estimating truncation error throughout the discussion, it may not be clear to you how the expansion can actually be applied to numerical methods. So recall that the objective of both examples were to predict the value of x as a function of x. That is, we were in determining function of x as specified by equation 4.5. So the function of x can be expanded in a Taylor series as shown in the continuation figure of equation 4.7. Now let us truncate the series after the first derivative term. So the function of x sub I plus 1 is equal to the function of x sub I plus the first derivative of the function x sub I multiplied by the function of x sub I plus 1 minus x sub I plus the remainder. Equation 4.13 can be solved for the first derivative of the function of x sub I equals to the function of x sub I plus 1 minus the function of x sub I all over x sub I plus 1 minus x sub I minus the remainder all over x sub I plus 1 minus x sub I as shown in equation 4.14. So the first part of equation 4.14 is exactly the same relationship that was used to approximate the derivative in our previous example. And equation 4.14 is given a formal label in numerical method. It is called the finite divided difference. It can be represented generally as equation 4.17, the first derivative of x sub I is equals to the function of x sub I plus 1 minus the function of x sub I all over x sub I plus 1 minus x sub I plus O function of x sub I plus 1 minus x sub I as shown in equation 4.17 and can be also represented as the first derivative of the function x sub I is equals to delta f sub I all over h plus O function of h, wherein delta f sub I is referred to as the first forward difference and h is called the step size, that is the length of the interval over which the approximation is made, and O function of h is the error of the step size. So we have here figure 4.6, the graphical depiction of a forward, backward, and center finite divided difference approximation of the first derivative. It is termed a forward differences because it utilizes data from x sub I and x sub I plus 1 to estimate the first derivative as shown in figure 4.6a. So the entire term of f over h is referred to as the first finite divided difference. So this forward divided difference is but one of the main needs that can be developed from the Taylor series to approximate derivatives numerically. For example, a backward and center difference approximation of the first derivative can be developed in a fashion similar to derivation of equation 4.14. So, the backward finite divided differences utilizes x sub I minus 1 and x sub I as shown in figure 4.6b, whereas centered finite divided differences uses values that are equally spaced around the point. So this is the certain point at which derivatives are estimated. So it uses x sub I minus 1 and x sub I. So it will have a step size of 2h. More accurate approximation of the first derivative can be developed by including higher order terms of the Taylor series. Finally, all the above versions can also be developed for second, third, and higher derivatives. So the Taylor series can be expanded backward to calculate the previous value on the basis of the present value as in equation 4.19. The function of x sub I minus 1 is equal to the function of x sub I minus first derivative of the function x sub I h plus the second derivative of the function x sub I all over 2 factorial h squared and so on until the nth term. Truncating this equation after the first derivative and rearranging, it will have the first derivative of the function x sub I congruent to the function of x sub I minus the function of x sub I minus 1 all over h, wherein O function of h is the error of the step size and inverse delta of f sub I is referred to as the first backward difference, and h is the step size, that is the length of the interval over which the approximation is made. A third way to approximate the first derivative is to subtract equation 4.19 from the forward Taylor series expansion to yield the function of x sub I plus 1 equals to the function of x sub I minus 1 plus 2 the first derivative of the function of x sub I h plus 2 the third derivative of the function x sub I all over 3 factorial h cubed plus so on, which can be solved for the first derivative of the function x sub I equals to the function of x sub I plus 1 minus the function x sub I minus 1 all over 2h minus the third derivative of the function x sub I all over 6h squared minus so on and so forth. Or it can be presented by the equation 4.22, first derivative of x sub I equals to the function of x sub I plus 1 minus the function of x sub I minus 1 all over 2h minus OH squared. Notice that the truncation error is of the order h squared in contrast to the forward and backward approximation that were in order of h. Consequently, the Taylor series analysis yield the practical information that the center difference is more accurate representation of the derivative as shown in figures 4.6c. For example, if we have the step size using a forward and backward difference, we would approximately have the truncation. Whereas the center difference, the error would be quartered. Equation 4.22 is a center difference representation of the first derivative. So in order to clearly understand the discussion about finite or finite divided differences, approximation of derivatives, so let's have an example. Example 4.4, finite divided difference, approximation of derivative. Problem statement, use forward and backward difference approximation of OH and the center difference approximation of OH squared to estimate the first derivative of the function negative 0.1 x to the fourth minus 0.15 x cubed minus 0.5 x squared minus 0.25 x plus 1.2 at x equals to 0.5 using step size h equals to 0.5. Repeat the computation using h equals to 0.25. Note that the derivative can be calculated directly as the first derivative of 0.4 x cubed minus 0.45 x squared minus 1x minus 0.25 and can be used to compute the true value as the first derivative of the function wherein x is equals to 0.5 is equals to negative 0.9125. So for the solution, for h equals to 0.5, the function can be employed to determine. So the function of x sub I is equals to 0.5. So x sub I minus 1 will be based on the given step size of 0.5. So we will have the x sub I minus 1 equals to 0 and x sub I plus 1 will be 1. So we will be able to find the function of x sub I minus 1 represented as 1.2, then the function of x sub I as 0.925, and the function of x sub I plus 1 equals to 0.2. So these values can be used to compute for the forward divided difference as equation 4.17. And equation 4.17 is represented by the first derivative of the function x sub I equals to delta f sub I all over h plus the error OH. So it uses the function of x sub I plus 1 minus function of x sub I all over the step size h. So from the given step size, 0.5, so substitute the value. So we have 0.2 minus 0.925 all over 0.5. We will have the first derivative of 0.5 equals to negative 1.45. Wherein epsilon sub t true percent relative error is equal to 58.9%. And continuation of the solution, for the backward divided difference, it is from the equation 4.20. And equation 4.20 represents the first derivative of the function of x sub I is equals to the function of x sub I minus the function of x sub I minus 1 all over h, or simply referred to as the inverse delta of f sub I all over h. It will have a value of negative 0.55. We will be able to find the true percent relative error of 39.7%. And for a center divided difference, so it will be from the equation 4.22 represented by the first derivative of the function x sub I is equals to the function of x sub I plus 1 minus the function of x sub I minus 1 all over 2h minus OH squared. So OH squared is the error of the truncation h squared. First derivative of 0.5 will be negative 1. Therefore, we will have a true percent relative error of 9.6%. So, same process will be applied for the interval of h equals to 0.25 will be represented as, so from x sub I of 0.5, subtract the data by 0.25, we will have 0.25 as x sub I minus 1 and 0.75 as x sub I plus 1. So the function of x sub I minus 1 will be 1.10351563 and the function of x sub I will be 0.925 and the function of x sub I plus 1 will be 0.63632813. So in continuation of the solution, the dataset on the previous slide will be used to compute the forward divided difference. So the forward divided difference formula, the first derivative of x sub I is equals to the function of x sub I plus 1 minus the function of x sub I all over x sub I plus 1 minus x sub I, which can also be represented by a delta f sub I all over h plus OH. So it will have a value of negative 1.155, which will have a 2% relative error of 26.5%. And for the backward divided difference, it will be the first derivative of x sub I equals to the function x sub I minus the function of x sub I minus 1 all over h, or represented by inverse of f sub I all over h, which will have a value of negative 0.714, which will have a true percent relative error of 21.7%. And the center divided difference will be the first derivative of the function x sub I equals to the function of x sub I plus 1 minus the function of x sub I minus 1 all over 2h. So h is equals to 0.25, so 2h will be 0.5. And it will have a value of negative 0.934 with true percent relative error of 2.4%. So for both step sizes, the centered difference approximation is more accurate than the forward and backward differences. Also, as predicted by the Taylor series analysis, halving the step size approximately halves the error of the backward and forward differences and quarters the error of the centered differences. So, let's try using Excel applying the finite divided difference approximation of derivatives. So, we're now going to use Excel applying the finite divided difference approximation of derivatives based on example 4.4. So we have here the given step size 0.5 and the value of x that we are estimating in order to find the derivative using the finite divided differences is 0.5. So therefore, the value of x sub I will be 0.5 and the value for x sub I minus 1 will be 0.5 minus the step size, and this will have plus the step size. So we will now have here the representation of the value of x. And we're now going to find the value of the function x sub I. So you have to take note, this will be the representation x sub I minus 1, x sub I, and x sub I plus 1. So this will be for the function of x sub I minus 1, the function of x sub I, and the function of x sub I plus 1. So in order to find the value of the functions, so we need to substitute the value of x to the function of x given. So it will be negative 0.1 multiplied by x raised to 4 minus 0.15 multiplied by x raised to 3 minus 0.5 multiplied by x squared minus 0.25 multiplied by x plus 1.2. And apply the process to all the value of x, we will have the value of 0.925 and 0.2 respectively. So after finding all the values, so we will now going to apply the forward, backward, and centered divided difference in order to approximate the derivative. So in order to clearly understand where does the series of equations were from, for the forward representation, we were given of first derivative of the function x sub I equals to the function of x sub I plus 1 minus the function of x sub I all over the step size h. If you recall the Taylor series, forward finite divided difference, so the function of x sub I plus 1 is equals to the function of x sub I plus the first derivative of the function x sub I multiplied by h plus the second derivative of the function x sub I, h squared over 2 factorial until the nth derivative of the function x sub I all over n factorial multiplied by h raised to n plus the remainder r sub n. So since we're going to find the first derivative of the function of x, we're just going to use this part of the representation of the Taylor series. So it will be the function of x sub I plus 1 equals to the function of x sub I plus the first derivative of the function x sub I h. And rearrange the equation, we will have the function x sub I plus 1 minus the function of x sub I equals to the first derivative of the function x sub I. And divide it by both sides by h. So we will have this particular representation of the first derivative. So we will now be able to find the first derivative of the function of x wherein x is equals to 0.5, applying forward finite divided difference for a first derivative only. Okay, so it will be first derivative x sub I equals to the function of x sub I plus 1 minus the function of x sub I all over the value of h. So we all know h can also be represented as x sub I plus 1 minus x sub I. So we will be able to find the value of negative 1.45. And based from the given derived first derivative of the function, and we all know that the true value of the first derivative of the function x sub I wherein x is equals to 0.5 is negative 0.4 multiplied by x cubed minus 0.45 multiplied by x squared minus 1 multiplied by the value of x minus 0.25, which will have a value of negative 0.9125. So we will now be able to find the epsilon sub t. So it will be true value, approximated value divided by the true value multiplied by 100. So we were now able to have the value of 58.9% true percent relative error of the first derivative of the function applying forward finite divided difference. So now let's apply the backward finite divided difference in order to find the first derivative. So in order to develop a backward difference approximation of the first derivative, so we're going to use x sub I minus 1 and x sub I. So it will be the function of x sub I minus 1 will be equal to the function of x sub I minus the first derivative of the function x sub I h plus the second derivative of the function x sub I all over 2 factorial h squared minus so on and so forth. And truncating the equation, since we're finding for the first derivative, so we're going to use this term in order to find the approximate value of the first derivative of the function. So it will be function of x sub I minus 1 equals to the function x sub I minus the first derivative of the function x sub I h. So rearrange function of x sub I minus 1 minus the function of x sub I equals to the negative first derivative x sub I h. So let's multiply both sides by negative 1 or just transpose all the equations in order to have a positive representation of the first derivative. So it will be first derivative x sub I h equals to the function of x sub I minus the function of x sub I minus 1 and divide all sides by h. So we will have the first derivative of the function x sub I equals to the function of x sub I minus the function of x sub I minus 1 all over h. So we will now be able to find the approximate value of the first derivative applying backward finite divided difference. So it will be the function of x sub I minus the function of x sub I minus 1 all over the value of h. So it will have a value of negative 0.55. So we will now be able to find epsilon sub t or the true percent relative error. So it will be true value minus the approximated value divided by the true value multiplied by 100. So it will have a value of 39.7%. So now applying the centered finite divided difference. So it will be, the value that we'll be having will be for the centered finite divided difference. So we will use here the function of x sub I plus 1 will be equal to the function of x sub I minus 1 plus 2 multiplied by the first derivative of the function x sub I h plus 2 the third derivative of the function x sub I all over 3 factorial h cubed until the nth value. So that will be the equation that we'll be using. And since we're finding for the first derivative using centered finite divided difference, we're just going to use this. We will now have the equation of the function x sub I plus 1 equals to the function of x sub I minus 1 plus 2 the first derivative of the function x sub I all over h. So rearrange the equation. We will have the function x sub I plus 1 minus the function x sub I minus 1 equals to the first derivative of the function x sub I h. And divide both sides by 2h. So we will have the first derivative of the function x sub I equals to the difference of function x sub I plus 1 and the function x sub I minus 1 all over 2h. So this will be the equation that we will be using finding the estimated value of the first derivative of the function using centered finite divided difference. So we will now be able to find the first derivative of the function. So it will be the function of x sub I plus 1 minus the function x sub I minus 1 all over 2 multiplied by h. So it will have a value of negative 1. And we will now be able to find the true percent relative error. So true value minus the approximated value all over true value multiplied by 100. So we will have the value of 9.59% relative error. So we're now going to apply the same process using h equals to 0.25. So based from the example 4.4, try using 0.25 interval. And this will now be the representation of the function x sub I minus 1, the function x sub I, and the function x sub I plus 1. So substituting the data, so we're still finding for the approximate value or estimated value of the first derivative of the function of x wherein x is equals to 0.5. So we're just going to apply the same formula. So this will be the values that we'll be able to calculate. So we will have here negative 1.15469, which will have a error of 26.54%, and negative 0.71406, 21.75%, and negative 0.93438, which will have an error of negative 2.39%, which is the same calculated values in example 4.4 from our PowerPoint presentation. So we're now done using Excel applying finite divided difference approximations of derivatives. Besides first derivatives, the Taylor series expansion can be used to derive numerical estimates of higher derivatives. So to do this, we write the forward Taylor series expansion for the function of x sub I plus 2. So we have function of x sub I plus 2 is equals to the function of x sub I plus the first derivative of the function x sub I 2h plus the second derivative of the function x sub I over 2 factorial multiplied by 2h squared and so on. So equation 4.21 can be multiplied by 2 and subtracted from equation 4.23 to give the function of x sub I plus 2 minus the function of x sub I plus 1 equals to the negative function of x sub I plus the second derivative of the function x sub I h squared so on. Can be used in order to find the second derivative of the function x sub I. So it will be the function of x sub I plus 2 minus 2, the function of x sub I plus 1 plus the function of x sub I all over h squared plus the error. This relationship is called second forward finite divided difference. So similar manipulation can be employed to derive a backward version. So it will be the second finite divided difference of the function x sub I equals to the function of x sub I minus 2, the function of x sub I minus 1 plus the function of x sub I minus 2 all over h squared plus the error of the step size. And a centered version of the second derivative of the function x sub I equals to the function of x sub I plus 1 minus 2, the function of x sub I plus the function of x sub I minus 1 all over h squared plus the error of step size h squared. As was the case with the first derivative approximation, the centered case is more accurate. Notice that the centered version can be alternatively expressed as the second derivative of the function x sub I is congruent to the function of x sub I minus the function of x sub I all over h minus the function of x sub I minus the function of x sub I minus 1 all over h all over h. So, you will notice the second derivative is similar to the resulted second order finite divided difference applying Newton's divided difference of interpolating polynomial. Thus, just as the second derivative is a derivative of a derivative, and the second divided differences approximation is the difference of the two first divided differences. So, we will now return to the topic of numerical differentiation. So, we have introduced the topic at this point because it is a very good example of why the Taylor series is important in numerical methods. In addition, several of the formulas introduced will be employed. So, recall that we employ Taylor series expansion to derive finite divided difference approximations of derivative, wherein we develop forward, backward, and centered difference approximations of first and higher derivatives. Recall that at best, this estimate had errors that were OH squared, that is, their error were proportional to the square of the step size. This level of accuracy is due to the number of terms of the Taylor series that were retained during the derivation of this formula. So we will now illustrate how to develop a more accurate formula by retaining more terms. So as noted, high accuracy divided difference formula can be generated by including additional terms from the Taylor series expansion. So for example, forward Taylor series expansion can be written as the function of x sub I plus 1 is equals to the function of x sub I plus the first derivative of the function x sub I h plus the second derivative of the function x sub I all over 2h squared until the nth term, which can be solved for the first derivative of the function x sub I is equals to the function of x sub I plus 1 minus the function of x sub I all over h minus the second derivative of the function x sub I all over 2 multiplied by h plus the error of the step size h squared as represented by equation 23.2. We truncated this result by excluding the second and higher derivative terms and were left with a final result of the first derivative of the function of x sub I is equals to the function of x sub I plus 1 minus the function of x sub I all over h plus the error represented by equation 23.3. In contrast to this approach, we now retain the second derivative term by substituting the following approximation of the second derivative. So you can recall equation 4.24. So we will now have the second derivative of the function x sub I equals to the function x sub I plus 2 minus 2 function of x sub I plus 1 minus function x sub I all over h squared plus the error representing equation 23.4. And after substitution to the equation 23.2, we will be able to yield the first derivative of the function of x sub I is equals to the function of x sub I plus 1 minus the function of x sub I all over h minus the function of x sub I plus 2 minus 2, the function of x sub I plus 1 minus the function of x sub I all over 2h squared h plus the error, or by collecting terms. So we will now be able to have the first derivative of the function equals to negative function of x sub I plus 2 plus 4 function of x sub I plus 1 minus 3 function of x sub I all over 2h plus the error represented by equation 23.5. So notice that the inclusion of the second derivative terms has improved the accuracy of OH squared. Similar improved versions can be developed for the backward and centered formulas as well as the approximations of the higher derivatives. So the formulas are summarized in figure 23.1 through 23.3 along with the results. So this is the figure 23.1. So for forward finite divided difference formula, so two versions are presented for each derivative. So the latter version incorporates the more terms of the Taylor series expansion, consequently more accurate. So this is for the first part that we have applied in example 4.4. So all of the first equation of each derivative are based from finite divided difference approximation of derivatives. The second one is that we're going to apply in numerical differentiation. So this is only the derivatives of each function from first to fourth derivative. So you can recheck by applying the derivation process. So you have to take note this is only for forward finite divided differences formulas from first derivative to fourth derivative. So the figure 23.2, so it will be for the backward finite divided differences formulas. So these are the two versions from first derivative to fourth derivative. We also use this formula in example 4.4. You can try to have your own derivation and you will also derive in this series of results. And the last figure, so we will have here the centered finite divided difference formula of the two versions from first derivative to the fourth derivative, applying centered finite divided difference formula. In order to clearly understand high accuracy differentiation formulas, let's have an example. Example 23.1. High accuracy differentiation formulas. Problem statement. So recall that in example 4.4, we estimated the difference of the function given as negative 0.1x to the fourth minus 0.15x cubed minus 0.5x squared minus 0.25x plus 1.2 wherein x is equals to 5 using finite divided difference step size of 0.25. You will recall that we have calculated series of values and its relative error wherein the errors were computed on basis of true value. So we're going to repeat this computation but we're going to apply the high accuracy formula from figures 23.1 to 23.3. Solution. So the data needed for this example is, so we're going to have the data from x sub I to the positive x sub I plus 2 up to the lowest x sub I minus 2. Based on the step size and we have the value of x equals to 0.5, we're going to subtract 0.25 values twice. So up to this, so we will have 0.25 and 0. And add 25 and we will have this series of value and substitute values of x to the function, have this series of related values. Applying the forward finite divided difference accuracy computed based on figure 23.1. When figure 23.1 represents the first derivative of the function x sub I equals to negative of x sub I plus 2, 4 multiplied by function of x sub I plus 1 plus 3 multiplied by the function of x sub I over 2h. We're now going to substitute the values in order to find the first derivative of the function applying forward difference of accuracy using high accuracy differentiation formula. So we will have negative 0.2 plus 4 multiplied by 0.6363281 minus 3 multiplied by 0.925 all over 2h, 2 multiplied by 0.25 equals to negative 0.859375 with an error of 5.82%. So applying backward difference accuracy using high accuracy differentiation formula in order to find the first derivative of the function of x wherein x is equals to 0.5. So figure 23.2 represents the first derivative as first derivative of the function x sub I equals to 3 multiplied by the function x sub I minus 4 multiplied by the function x sub I minus 1 plus the function x sub I minus 2 all over 2h. Substituting the values, we will have negative 0.878125 with a value of the error as 3.77%. Continuation of the solution. So the centered difference of accuracy is computed as based from the figure 23.3, wherein the first derivative of the function of x sub I is equals to negative function of x sub I plus 2 plus 8 function of x sub I plus 1 minus 8 function of x sub I minus 1 plus the function of x sub I plus 2 all over 12h. And we will have the value of negative 0.9125. And you will notice it have a 2% relative error of 0%. So as expected, the errors for the forward and back differences are considerably more accurate than the result from example 4.4. However, surprisingly, the centered difference yields a perfect result. So this is because the formula based on the Taylor series are equivalent to passing polynomials through the data points. So let's try using Excel applying higher accuracy differentiation formulas in order to find the approximate value or estimated value of the first derivative of the function wherein x is equals to 0.5. Okay, so we're going to use Excel applying high accuracy differentiation formulas. So you will notice that I am using the same Excel sheet, and we are going to have comparison of finite divided difference, approximation of derivatives with high accuracy differentiation formula. We're going to find here the first derivative for forward, backward, and centered. And you will see the difference in the formula. So these are the formula for the finite divided difference, and these are the formula for high accuracy differentiation formula. So you will notice that the difference is it already has x sub I plus 2 and x sub I minus 2. So using the same values, the only difference is we need to add the two data sets. And what are these? So it will be the x sub I minus 2 and x sub I plus 2. And it will be based from x sub I minus 1, subtracting the step size, and again, adding the step size. So we will now have the value of the function for x sub I minus 2 and x sub I plus 2. So the representations are x sub I minus 2, x sub I minus 1, x sub I plus 1, x sub I plus 2. So this is the function of x sub I minus 2, function x sub I minus 1, function x sub I, the function of x sub I plus 1, function of x sub I plus 2. So substituting all the calculated values to the formula of high accuracy differentiation formulas, so we will now be able to find the first derivative of the function of f wherein x is equals to 5. And we all know that the true value of the first derivative of the function of x wherein x is equals to 0.5 is negative 0.9125. So we're now going to have here negative function x sub I plus 2 plus 4 multiplied by the function x sub I plus 1 minus 3 multiplied by the function x sub I all over 2 multiplied by the value of the step size. So we will now have here the value of negative 0.859375. And for the true percent relative error, so true value minus approximated value divided by true value multiplied by 100. So it will have 5.82% relative error with respect to the true value. So now we're going to have the value of the first derivative using backward high accuracy differentiation formula. It will be 3 multiplied by the function x sub I minus 4 multiplied the function of x sub I minus 1 plus the function x sub I minus 2 all over 2 multiplied by h. So it will be true value minus the approximated value divided by the true value times 100. And we will have a value of 3.77%. So now using centered finite divided difference, using high accuracy differentiation formula, so it will be negative the function of x sub I plus 2 plus 8 multiplied by the function x sub I plus 1 minus 8 multiplied by the function x sub I minus 1 plus the function of x sub I minus 2 all over 12 multiplied by the step size of h. So we will now have the value of negative 0.9125. We will now be able to have here calculated value of 0%. So in comparison to the finite divided differences result from example 4.4, so you will see that high accuracy differentiation formula is more accurate than the finite divided difference formula since it uses an additional value of data points. And also, the error are considerably more accurate. So, you will see it has only a 1-digit errors in compared to 2-digit errors in previous calculation. And surprisingly, at the centered finite divided difference using higher accuracy differentiation formula, it yields a perfect result. So, with a 0% error, unlike the previous calculation which has a 2% error. We're now done using Excel applying high accuracy differentiation formulas.